Hi, Algebra 2 students. This is Ms. Penn. Today's notes are on operations with radical expressions. And we've been doing a little of this already, and I'm just going to kind of formalize what we've been exploring in class with some examples. So first of all, I just want to kind of formalize two rules or properties we've been following when we're manipulating radicals or expressions with rational exponents. And the first one is the product property, which basically says if you have the nth root, so it doesn't have to be a square root, it could be any root of a product, say a times b, then that will always be equivalent to the nth root of a times the nth root of b, right? And this is what allows us to simplify radical expressions. The second rule is the quotient rule. Quotient means division, right? So if you have the nth root of a divided by b, it says that that is equivalent to the nth root of a divided by the nth root of b. So we're going to kind of be using both of those rules to kind of help us when we're simplifying. So all of these first examples, we're going to be trying to simplify the radical expressions. So the first one is the cubed root of 135. And so the idea is we'd like to know, like, is there something cubed inside of 135? Like, is one of the factors of 135 appear 3 times? So the one way we can do this manually would be to do, like, for 135, nothing immediately pops into my head. So then I could do like a factor tree, prime factorization. So you can think, what times what is 135? I know 45 times 3, and then 45 can be broken down into 9 and 5. 9 can be broken down into 3 times 3. And then 5 can't, these are all now prime numbers, right? They have 3 3s and a 5, and that's telling us, so basically like anything at the end of the tree is one of the factors. So that's telling us that 135 is the same thing as 3 times 3 times 3 times 5. Now, this helps us because now I can see, oh, this 3 times 3 times 3, that's really like a 3 to the third, which means I can rewrite this as the cubed root of 3 to the third times the cubed root of 5. So I'm kind of separating my perfect cube away from the other piece of the factor. And so the third root of 5 is going to stay inside the root, but the third root of 3 to the third, those cubes are going to, the cube and the cube and then this is like a 1/3 exponent are going to cancel each other out. So then we're left with 3 times the third root of 5. Okay? Now, there is a trick you can do on the calculator. And so the calculator trick to tell you like what number belongs outside, what number belongs inside, is that for some radical, the nth root of a, if you go to a graphing type calculator and in y equals, if you put in a over x to the n, so you want to use the specific a and n values in your problem, then going to the table will allow us to see what number belongs inside the root, what number belongs outside the root. So like in this example, I would do y equals, a in this case is 135, divided by x to the third, because it's the third root. And if I pull up my calculator and actually type this in, 135 divided by x to the third, when I go to look at my table of values, I'm looking to see where are their whole numbers in both the x and the y. So I have like 1 and 135, but that's kind of like the trivial situation. So then if I scroll down, I see 3 and 5. So that is telling us, the x value is telling us what number can come out of the root. So, right, because if you look here, this 3 is that 3, and then the 5 is that 5, okay? So in the table of values, right, you have an x and a y. So I'm just going to kind of, for our reference, we had in this case 3 and 5, and that 3 is going outside the root. Because the idea is like in this equation, 3 cubed is divisible by 135. So that's 3 is going to come out, and then the 5 is what's left over. So we get 3 with the 5 inside, and it's a cubed root. Okay? So you can always do that if you have a graphing calculator handy, and that will always give us the right answer for simplifying numerical roots. Okay, so let's look at another example. The next example has variables in addition to numbers. So we can kind of think about the variables and the numbers separately. So for this is the fourth root of 48 times a to the 7th, right? So I can break that down into the two different parts and then think about how each part simplifies. So with 48, so I could do a factor tree again. I know that's 4 times 12. I know 4 is 2 times 2. 12 is 2 times 6. And then 6 is 2 times 3. So then I get 2, 2, 2, 2, 3 as my prime factorization. So that would be 2, right? And what I'm looking to take out is, since it's the fourth root, I'm looking to see if there's any perfect to the fourth power. So do I have 4 of the same root? I have 1, 2, 2, 2. So I have 1, 2, 3, 4 2s. So that's going to help me out because I know that would be the same as 2 to the fourth power. So now the idea would be coming over here, I can say this is going to be equivalent to the fourth root of 2 to the fourth power times 3. I'm going to do something similar with the a to the 7th, right? Because a to the 7th is the same thing as a to the 4th times a to the 3rd. So I'm breaking this down by I'm trying to get as many something to the 4th powers as possible. And then this a to the 3rd is what's left over because 4 plus 3 is 7. The exponent rule trick would be to say that if we convert this a to the fourth root of a to the 7th into a rational exponent, and then we turn that rational exponent into a mixed number. So we say, how many times does 4 go into 7? It goes in 1 time, right? And then there's a remainder of 3, so that's like 1 3/4. Then we can kind of pull that apart, so that gives us a to the 1 times a to the 3/4. So the idea is that 1 is telling you what's going to come out of the root, and the 3 is telling you how many are left over in the root. So then this would get simplified to a, the fourth root of a to the 3rd. So like here, we're going to see the same thing happen because the a to the 4th I've written here is going to get canceled with the 1/4 exponent, and the a to the 3rd is going to stay inside the root. So to finish this problem, we see, okay, what comes out of the root is anything that has a perfect to the 4th power. So what's going to come out is a 2a, since 2 to the 4th and a to the 4th. And then what's left over inside the root is the 3a to the 3rd. So moving on to our next example. In this example, we're actually going to get to use the quotient rule now because we have a division right here. So I can kind of apply the square root to the 64 and the 81 separately, and that's kind of nice because those are both perfect squares. And now I'm going to need to also think about what's going to happen to each of these variables. Okay, so first of all, with the numbers, I'm going to get the square root of 64 is 8, the square root of 81 is 9. And then with my variables, well, the square root of q squared, well, the square root and the squared are going to cancel, so that q is going to come out of the root. P has an exponent of 1, right? So nothing can come out. There are no p squareds within p to the first power, right? So that I know for a fact that p is going to stay inside of the root. And then with r to the 5th, well, I know r to the 5th. So if I do the division rule, it would say do 5 over 2, which is 5 goes into 2 twice with the remainder of 1. So that would tell us that within r to the 5th, an r squared from that 2 right there could come out, and then the exponent left inside is the numerator of the fraction, right? So then that means there's an r left over inside. You can also do it by saying r to the 5th is equal to r squared squared times r, and then you know like this squared will cancel, so what's going to come out is the r squared, and then what's going to be left over inside is this r. From here, I'm like looking to see, can I simplify this further? 8/9 doesn't simplify, so it looks like this would kind of be my final answer. I could write it all as one fraction, so I could do 8qr squared root pr divided by 9. And that looks a little bit nicer than what I had before. So with this next example, example 4, I'm moving into some more operations on radicals. So the first 3 examples were more just simplifying radicals, and now we're going to see how simplifying interacts with addition, multiplication, and division, and subtraction. Okay, so the idea here is we can always combine like radicals. So like if the roots are the same, then we could add the numbers outside the same way we would do with like 2x plus 3x is 5x with combining like terms. So it's very similar to that. And the idea is that you need to simplify these roots to see if any of them have a radical in common. Because I'm thinking like 50, the square root of 50 is not the same as the square root of 500, but maybe some piece of each of these roots can come out, and what's left over will be the same. Okay, so that's like what the kind of big idea here. And so what I'm going to do is think about how each radical breaks down. So I know, I'm thinking like, are there any perfect squares in 50? I know that's 25 times 2, right? So I could rewrite this as the square root of 5 squared. I'm just writing it in exponential form, but 5 squared is 25 times 2, right? I'm going to bring down that 2 out front. I'm going to do the same thing for the next one. So I know that's equivalent to, well, 500 would be 100 times 5, right? 100 would be the largest perfect square here. So that means 100 is 10 squared times 5, like that. Let me zoom in a little bit. And then similarly, I have 6, and then the square root of 125. So I know 125 is 5 times 5 times 5. So I'm going to say that is 5 squared times another 5. And I'm specifically saying squared because this is the square root. So I know if I can write something raised to the second power, it's going to cancel, right? So now let's see what comes out. So from the first radical, the square root of 5 squared is 5. So a 5 would come out, get multiplied by that 2, and we get 10 root 2 plus here the square root of 10 squared is 10. So that means a 10 will come out and get multiplied by the 4, so we'll get a 40 here. And what's left over inside is just the 5. And then we have minus the square root of 5 squared is going to be 5 coming out, right? Oops. So that means that 5 will get multiplied by 6 to get a 30 here, and what's left over inside would be this other stray 5 right here. Okay, so now what I'm looking to see is, do any of these have the same number inside of the root? Because if they do, I can combine like terms. So I'm going to kind of write a little note for ourselves. Combine like, I'm putting terms in quotes. And really what I mean when I say terms is radicals. So the radicals that are in common is that we have 2 kind of radical 5s, right? So that means this one can't get combined with anything, so I'll just stay the same and be 10 root 2. But here I can do 40 root 5 minus 30 root 5 to get 10 root 5. So I didn't change the number inside the roots, I just subtracted 40 minus 30 to get 10. Okay, and this would be my final answer. Okay, moving on to the next example, we have a multiplication problem now. So a multiplication of like radical binomials. I'm saying binomials, it has 2 terms. It works exactly like multiplying binomials with variables, where you do FOIL, or you could do the distributive property, or you could do the box, whatever you prefer. I'm going to do FOIL, just for that's what I prefer to do right now. So if I do 2 to the root 3 times root 3, so I'm just going to kind of write that down exactly as I see it, and we'll think about how it simplifies. And then I have to do 2 times root 3 times 2 times root 2. So I'd say plus 2 root 3 times 2 root 2. And then I want to do the same thing with the second term, right? So I do minus 4 root 2 times root 3. And then minus 4 root 2 times 2 root 2. Now I'm going to see how all this multiplies out. So anytime I have the square root twice, right, that's going to kind of become like, this is going to become right here root 3 squared. So the squared and the root cancel, or you could think of it as 3. This is the same thing as the square root of 3 times 3, which is 9, and the square root of 9 is 3. But either way, this is going to become a 3 times 2. So we get 6. Okay. And then here, I have 2 times 2, so that's 4, and then the square root of 3 times the square root of 2. So the product rule says that will be equivalent to the square root of the product of 3 and 2, which is 6. Okay, now moving on to my next term, I have minus 4, and then times root 2 times root 3 would be root 6 again. And then for my last term, I have 4 times 2, and I have a root 2 times a root 2 also. So remember that this root 2 times this root 2 is going to just become a 2. So I would get 4 times 2 times this 2, and I get 16. So that's a negative 16. All right, so now I'm going to keep simplifying, and I see I have 2 terms with a root 6. And they both have, this one has a 4, this one has a negative 4, so that's going to cancel. So 4 root 6 minus 4 root 6 is 0, right? And now 6 minus 16 is negative 10, and that would be my final answer. Okay, one last example for you today is with division. So dividing radical expressions is very similar to dividing when we're using imaginary numbers, because we're trying to get, like when we're dividing imaginary numbers, we don't want an I in the denominator. When we're dividing radical expressions, we don't want a radical in the denominator. So the way we get rid of it is by multiplying by the conjugate of the denominator. Let me zoom out. Multiply by the conjugate of the denominator. Now, do you remember what a conjugate is? A conjugate is if you have A plus B, then the conjugate would be just switching out the plus sign for a minus sign. And the reason this is special is because we use this to our advantage, because we know that A plus B times A minus B, that's the difference of 2 squares, A squared minus B squared. So this allows us to kind of cancel out the square roots. Okay, so let's see how it works in action. So the idea would be I would multiply top and bottom here by the conjugate of the denominator, which would be 3 minus root 5. 3 minus root 5. And what happens in the denominator is this. I know I could FOIL it out or use the box, but I could also just use this trick. So I know that this is always going to equal, I'm going to do my denominator first. So A squared minus B squared. My A squared would be 3 squared, and my B squared would be root 5 squared. In my numerator, I actually need to do the FOIL completely out. So I would do 2 times 3 is 6. 2 times negative root 5 is negative 2 root 5. And then I do negative root 5 times 3 is negative 3 root 5. And negative root 5 times negative root 5 would be positive 5. Let me extend that. Okay, now I'm looking to see how everything simplifies So I can see on the bottom, 3 squared is 9, and then root 5 squared would just be 5, so 9 minus 5. On the top, I have 6 and 5 make 11, and then negative 2 root 5 and negative 3 root 5 make negative 5 root 5. So last step would just be to do 9 minus 5 and get 4 as our denominator. And this would be the most kind of simplified version of the radical expression. I could look and see if like anything divides out between 4, 11, and 5, but it doesn't. So I'm done here. All right, so there are no U-tries in this video, but you do have some practice problems on the back of the worksheet from class today. See you guys tomorrow.